Okay, well, here we go, folks. My name is Jane. On behalf of live long and prosper. I'm very excited about this movie about protons, right? Salad? Protons. Always get those mixed up. My name is Jane. On behalf of our board of directors, our staff, our volunteer, and our members, welcome to the Colonial Theater. We are so happy to be a part of this Science on Screen series. This is finishing up this first section. I'm sure we'll do another section, maybe in the fall, don't know, definitely next year. So let me just say, enjoy your snacks. We are carry in, carry out. Please help us keep the theater tidy. We have a great presentation for you. Our July calendar will be out next week, so grab one of those. Grab one of our season programs. We got a full season going through November with some live shows. So anyway, I would like to introduce to you from Whimsy, Miss Emily Stanislavski. Woo! Hi, everyone.
That sounded very loud. My name is Emily Stanislavski, and I come to you from Whimsy, White Mountain Science, Inc. We are a STEM nonprofit based out of Littleton, and we go into schools, we have kids come to us, and we do all things STEM with both students and with teachers. And I am so very excited to introduce Dr. Elena Long. She's an assistant professor of physics at the University of New Hampshire, a recipient of the JSA Promising Young Scientist Award and the JSA Post-Doctoral Research Prize. Her research is on the very edge of nuclear physics and looks at the internal structure of protons and neutrons and how they come together to form atomic nuclei. Dr. Long is the founder and lead organizer of LGBT +physicists, an organization that seeks to build a scientific environment that is free from all forms of prejudice and discrimination. She is also the past chair of the American Physical Society's Forum on Diversity and Inclusion, which works towards creating a better, more welcoming physics environment from an intersectional lens. We are so excited to have Dr. Long here with us tonight to present her talk, Understanding the Nature of Matter with Polarized Targets.
Thank you so much for having me here this evening. Thank all of you for coming out and joining me this evening. Thank you to all of the wonderful folks behind the scenes who have made this happen. And given the fact that we are in Pride Month, happy Pride, and thank you to all of my LGBTQ brothers and sisters who came before me and fought for my rights such that I can stand before you today. I'm going to start this talk with what I found as a kid to be one of the most interesting things I learned about science. This was in, I think, late middle school, early high school, when I learned that most of what we're made of is empty space. We have electrons going around the atoms inside of us that make us up. And way in the middle of that, we have atomic nuclei made of protons and neutrons. And 99% of the stuff in between is just empty. Nothing there. It's fascinated me as a kid. And as I developed, went off and learned more, and ended up becoming a nuclear physicist, I ended up learning something else, that not only is most of us made of empty space, but most of the rest no longer exists by the time you think about it. It's a little bit, I'm putting an asterisk here. It's not quite entirely true because the energy is all there, but there's this giant mess of particle, antiparticles popping into existence, moving near the speed of light before disappearing again, that ends up being a lot of what we're made of. But in order to explain this big, messy, complicated picture, we need to take a little bit of a walk through history. So we're going to go through kind of a brief tour of over 100 years of nuclear physics, of how we got from point particle understanding of what these things are to this giant, complicated mess of where our understanding is today, and a little bit about the work that we are doing going forward to continue our understanding. So I'm going to start all the way back in 1913. We are in the realm of discovering the nucleus. The famous Rutherford experiment, his photo here and some of the folks he worked with, the scale of experiments was tabletop. This is something that you could easily fit on a benchtop. And the way that this experiment was done is actually really similar to how we still do experiments today. We have something of interest we want to study, so we call that our target. We have some kind of probe, which is some kind of other particle that can move, and we shoot one at the other and measure something coming out in a detector. One of the useful pieces of information to get out of this is energy transfer, so the difference between energy in compared to energy out. I'm going to call that new, so if that comes up, it's just saying how hard did I hit this thing? A few years later, comes 1917, World War I occurs. A lot of Rutherford's work gets diverted to the war effort, learning about radar, helping develop that. But when he came back into the laboratory, he continued his experiments and built this chamber here, where he has a source of radioactive material that can go through a chamber that was either pulled to a vacuum so there was nothing in it, or filled with nitrogen gas. And he put a magnet here because we can use the magnet to see if charged particles are coming through, because a charged particle will bend going through a magnetic field. The particles coming out of this source are alpha particles. They have some amount of charge with them, so they would bend through this magnet into a detector, which was him and his students looking in a telescope with like a little eyepiece, or through a microscope. Nitrogen is a lot heavier than alpha particles, so they don't bend as much. And this is what they were looking at studying. But what they found was a whole bunch of additional hydrogen atoms in here. And they would empty it out, fill it up again, empty it out, fill it up, and this hydrogen would not go away. This led to our discovery of what we now call the proton, that there is some subpart of nitrogen that breaks off. He was knocking protons off and seeing them coming out. While this work was being done, there's another man named James Chadwick who was spending that First World War in an internment camp, actually doing experiments in the camp with radioactive toothpaste, because this is the era of the radium craze. People are drinking Vitality, radioactive water, thinking it was good for it. Hint, it's not, don't do that, it's a bad idea. Anyway, after the war, he got released and actually ended up becoming one of Rutherford's students and working with him. He repeated a very similar experiment, so basically the same piece of equipment in the first place, and saw the same thing there. But what was new is he put a secondary detector some far distance away, but without that source inside of it. And what he found is that he was still getting hydrogen coming out of it. Where is this coming from? Why is this chamber still getting something knocked out of it? And his conclusion was there must be some other particle going through that has no electric charge. It is a neutral particle going through that we now call the neutron. So this is how we know that protons and neutrons exist. It was thought at the time that these may be point particles, fundamental pieces of nature that couldn't be broken up further. And in studying some of the weirdness of quantum mechanics, quantized spin was co-discovered by Otto Stern, who studied under Albert Einstein. Quantum mechanics, quantized, we're talking about discrete levels where something can only exist at them. So it can jump in between, but not be at a state on the in-between. So it just has these discrete quantized or quantum states. When we're talking about spin, we're talking about magnetic fields, basically. So we can consider these little protons and neutrons almost like little magnets. And by studying whether they are aligned with or against a magnetic field, these two possible quantized states can only be in one of two. There were measurements that he worked on, and what he found is that the magnetic moment, this magnetic property, was almost 3 times bigger than was expected at the time, thinking at the time that this was a point particle. This is the first hint that we have that the proton is made up of something else, that there's something smaller inside of it. Of course, now if we're kind of looking at the date, Otto Stern, along with many other scientists at the time, ended up fleeing Europe as Nazis rose to power and World War II happened, taking a huge amount of the amazing brilliance of scientists at the time and changing their efforts from understanding protons and neutrons and whatever is going on with this weirdness into building bombs. And following the end of the war, going into the beginnings of what followed, leading from atomic bombs to the much larger hydrogen bombs. Really, a lot of scientific effort went into that. But after things started calming down a little bit, our story kind of in understanding protons and neutrons picks up again. It picks up with a postdoc at the time, whose last name is Rosenbluth, who developed a method to try and understand what might be inside of protons and neutrons. He did this work in 1950 and actually later worked for Edward Teller. But what he looked at was a way to use what's called elastic electron scattering from nuclei to measure something called a cross-section. What the heck is a cross-section? Well, I mentioned before, we have some kind of target, we're going to hit it with some kind of beam, and we're going to detect something coming out of it. In the detector, how many things come out of it, we're going to call some number of events that we count in our detector. But what we care about are events that are related just to the physics of the interaction and nothing else. So one thing that is not necessarily related to the physics of the reaction, but would change the number of events, is if we look kind of zoom in right on the endpoint here, if we send twice as many particles in, you'd expect twice as many to come out, but that has nothing to do with the physics, so we have to get rid of that. Or if you have twice as many things that you're trying to hit, that would also affect that, so we have to get rid of that. These two pieces and some other similar things we put together in this term called luminosity that has this fancy L. So this normalized number of counts, we divide out luminosity because that has nothing to do with the physics, or just extra things. And the other piece of it is time. If I let this experiment run twice as long, I'll get twice as many events. It has nothing to do with the physics. So a cross-section is just taking that number of events and dividing it by the things that have nothing to do with the physics. Now comes Rosenbluth's idea of how we can interpret it. So before him, there was another guy named Mott who developed a cross-section that would describe point particles if there was no substructure. And Rosenbluth added additional terms that would describe deviations away from point light. So these would be starting to describe substructure inside of these things. A lot of these terms I've highlighted in peak here are, don't worry too much about them, they're related to how the experiment's set up. But these other two, GE and GM, that's where the interesting things come in, because that tells us about the electric and the magnetic structure of protons and neutrons. The electron scattering says that we are putting in electrons into this interaction. We mentioned nu before. I'm going to introduce a new variable called q squared. This is for momentum transfer. The important thing here is that if we go to higher q squared, we have better resolution. So you can think that higher q squared is like zooming in on a camera. You can get a higher resolution picture. A few years after this mathematical development happened, an experiment was put together to measure this. And a guy by the name of Robert Hofstadter at Stanford built experiments to test this new mathematical construct. He had really big expertise in detectors. In particular, he's kind of the guy who we can credit for making the detectors so students didn't have to look at these things with their eyes anymore. So thank you to Robert Hofstadter for that. This is kind of a picture of the size of these experiments growing. There's now a large beamline coming in, hitting a much larger target than these desktop ones, and going into what's called a spectrometer. But a spectrometer is basically just a fancy magnet with fancier detectors in it. It's the same basic process. Charged particle bends in a magnetic field, and we use that to learn things. If the proton was a point particle, it would be expected to go on this dashed line, this Mach curve. But the data that he found deviated from that curve. This is the first direct experimental evidence that proves the proton is made up of something smaller. In his paper for this, he noted that furthermore, nuclei are built up out of protons and neutrons, and it is fascinating to think of what the proton itself is built. He also has this interesting line of other interesting things to study. Deuteron's going to come up again. This is my everything bagel. We'll talk about that in a little bit. So diving in a little bit deeper, we now have a way of measuring these new properties. These GE, GM, these electromagnetic things, we call form factors. And we measure it versus Q squared. For ease, we compare these to dipoles. So the most familiar dipole you're probably familiar with is a bar magnet. It has a north pole and a south pole, 2 poles, dipole. If I were to plot a dipole structure on here, it would look like this pink line. And some interesting things happen where mostly this looks like a dipole, but if there's any part of this that isn't dipole-like, that means that there's something further that we don't understand, which is interesting new things to study. So remember, this magnetic moment for the proton was about 3 times larger than expected. This Rosenbluth technique using these form factors gave us the experimental proof of why this occurs. If these things are dipole-like, we can take the data here, divide it by the dipole model, and that should come out to exactly 1. And anything that deviates from 1 would be something not dipole-like, which as a physicist I would find very interesting. We also get higher resolution as we go to higher Q squared, which is what this is showing. And because this value is changing with Q squared, this is why this type of measurement directly indicates substructure, because as we go to higher resolution, we're seeing something changing. So there's something inside there. Using this technique, dividing it by 1, for the most part, this is pretty close to 1. Using this Rosenbluth separation technique, we use some fancy mathematics to this to tell us that the proton has a large positive core that kind of dies off as it goes around to the outside. We can learn something similar about the neutron. I didn't put it up here, but the neutron looked like it had a positive core with a negative cloud around the outside of it. These two things together are telling us that protons and neutrons are made of things that they themselves are charged. So learning more about this, we're going to introduce a new variable called x. This is a momentum fraction scaled to a proton. The way I want you to think about x is how big is the thing that we hit? So if x is equal to 1, 2, 3, if we're hitting carbon 12, x would be 12 if we hit the entire carbon nucleus. This is that elastic scattering I was talking about beforehand. If we instead hit a single proton or neutron, since this is scaled to 1 proton and they weigh pretty much the same, that would put us at an x of 1. And if we hit x smaller than 1, we enter into a region where we're hitting things inside of protons and neutrons. This deep and elastic region probes those things inside. So just like we had the form factors for elastic scattering, when we go to this new region, we have something very similar that are called structure functions. So once again, we have the point-like part and the structure part. What I'm going to start by looking at is this F21 first. So I'm going to leave F1 for a moment because F2 is really, really neat. Let me show you why it's neat. Isn't that neat? Of course, if you don't understand what's going on, maybe it's not so neat. So let's take a look at trying to describe this mathematically. Well, if we had a point particle, if the proton was a point, then this structure function at an x of 1, which is scaled to a full mass of a proton, we would get a really sharp peak right at 1. This doesn't even go to 1 because nothing happens out here. Instead, it's kind of coming, kind of eyeballing the peak, maybe about a third. So if it's at a third, that would indicate that what we're hitting is something that is roughly 1/3 of momentum distribution of what we're looking at. This is our first indication that these new particles called quarks, up, down, charm, strange, top, bottom, if you've ever heard those terms, this is our first indication that those exist. So we're at about the right peak, but we don't have any of this other structure. How do we get this spreading out? Well, if these point particles interact with each other, it kind of smears out what this interaction would look like. So if these quarks can interact, they're self-interacting, it spreads out this peak. Now we're starting to get pretty close, particularly on the right-hand side of this. Our model for what's inside these things is working well. but we're still missing something on the low end. This is where things get really cool. In order to describe this low end, to fill in what's happening here, the way that we can describe that is by updating our model to not just have these three interacting quarks, but by adding a quark C, a mass of a huge number of particle-antiparticle pairs that pop into existence for a brief moment of time, interact with these three stable quarks that we sometimes call valence quarks, and then re-annihilate after moving at a fraction of the speed of light inside of every single nuclei in every single atom of your body. That's pretty neat. If we want to continue learning about these things, we can learn more properties about these now found quarks with F1. This describes the magnetic interactions of quarks, that spin property I was talking about. If we have called spin half particles, that means they can be in two states, either plus 1/2, minus 1/2, and that's it, because quantize, only two. If that's true, then we would expect the two form factors to have this relationship. I'm going to do a little bit of algebra. Sorry about that. Rearrange it so it's equal to 1, because I like seeing things deviating from 1 to know if I understand what's happening. This relationship is known as the Caroline-Gross relationship for those who created it. And if we plot the data of this, lo and behold, it's right at 1. So these structure functions not only tell us that there are these quarks inside of protons and neutrons, and this quark-antiquark C, kind of this massive activity going around, it also tells us information about their spin that we can learn from. Now we're going to go forward a few decades into a new degree of freedom, to a new way of understanding protons and neutrons, utilizing that property of spin that I've been talking about. With polarization, what we can now do is directly manipulate the spins of nuclei sitting in some target. So we can take a whole bunch of protons and make them spin the same way, take that cross-section, and we can change the spin direction and do it again. What's really cool about that is we can do what are called asymmetries, where we take this cross-section difference over these two things added. This gives us relationships where we still have those experimental setup terms and those structure terms the same as we saw before, but what's really useful here is anything that's the same cancels out. So big bulk effects, or things that are going to make up the majority of the cross-section, completely cancel out in asymmetry, and what you're left with are more subtle effects that you can use to really understand what is happening at extremely small levels. This leads to the creation of laboratories such as Jefferson Lab, which is an accelerator in Virginia that I partner with for a lot of my experiments. The key point from here, the vast majority of everything that we as humans know about nucleons, the things that are the core of what make us up, are either from cross-sections, if we want to learn about bulk properties, or asymmetries, if we want to learn about tiny specific properties. So this is what the laboratories today look like. This is Jefferson Lab. It's an accelerator. This is a racetrack of about a mile, where we effectively have a lightning bolt going around this 5 times. So there's like 5-mile long lightning bolt that we're shooting into these targets to do these experiments. The number of people that work on them these days has grown tremendously, from the 2 or 3 people in those early days to hundreds of collaborators working on building them. And the scale is definitely not tabletop anymore. This is a detector that has roughly the footprint of a mobile home, is about 4 stories tall, and sits in a big underground cylinder that has a width of about a football field. This is the inside of this little hill here. So these polarized targets, we've had this older way of doing it, the Rosenblum separation I mentioned. I showed you those results already. We have this new asymmetry way that gives us more information about more subtle effects. And this should give us a more accurate way of measuring these things. And some of the early experiments at Jefferson Lab were to redo these GEGM to just make sure that the lab is working. And, well, here's that older one that looked really similar to 1, and here's this new method. And especially as we go to higher Q squared, there is this huge discrepancy between what we thought we knew looking at bulk effects and what we found out with asymmetries that are more accurate looking at more subtle effects. This led to an explosion of different theories: perturbative QCD, generalized parton distributions, quark angular momentum, a whole bunch of fancy science terms that all kind of came up to try and understand what is going on here. Looking back at structure functions, we mentioned before F1, F2, that told us a whole lot about what's inside these things. And now with this kind of sense of all these things going on, we can use this again, but now with polarized targets. So I'm going to rewrite this in a just slightly simpler form here. And if we go from an unpolarized target to a polarized target, we get new structure functions that don't exist for unpolarized targets. These are new things that we can measure to get us information to even more insight into what protons and neutrons and the things that make them up are doing. So one of these in particular, not quite asymmetry, we're just looking at putting a polarized target in two different states and looking at the difference. That gives us this first term here called G1. There's a lot of math here, but what I want to point out is this Q stands for the quarks, and this plus sign says that that quark is in a spin-up configuration, and this minus sign indicates a quark that is spin down. This structure function, which comes directly related from this measurement, gives us information about where quarks are inside of protons and neutrons with different spin states. Huge amount of data has been taken on this. Fascinating subject to really try and understand what's happening. We've learned about quark spin distributions, where things are, and what we've learned is that the valence quarks, those three things that are stable inside, the three ones that are there all the time, not this mess of things popping into and out of existence, but the three that are always there, they don't carry all of the proton spin. We're missing about 2/3 the spin in protons and neutrons that we don't know where it comes from. And we know that because of this G2 measurement telling us it. This problem, this ongoing issue in nuclear physics, we call the spin crisis because we don't know where all the spin's coming from. We just know it's not coming just from these three things, but some other contribution is coming from this big mess of activity going on inside. So where do we go from here? This is the work that I've been doing lately, is working on creating even new degrees of freedom to create new types of measurements to explore even more subtle effects. And I call this tensor-polarization. What the heck is tensor-polarization? So I mentioned polarization kind of generally. I'm now going to move into calling vector polarization. That's when we have spin up, spin down, and we look at spin up minus spin down. If we go to not just a spin half particle, but a spin one particle, we get a new degree of freedom. It can be spin up, spin down, or in a spin zero state. And the simplest nucleus we can put in this is called a deuteron. It is one proton, one neutron. And what I find neat about this is that the shape of that nucleus depends on its spin state. So if it's in either if it's either spin up or spin down, it looks like peanuts. And if it's in spin zero, it looks like a bagel. So normal polarization for this, my world, is basically looking at up peanuts minus down peanuts, which is not so much what I'm caring about these days. Rather, I'm combining the peanuts together and comparing them to my bagels. And if I have more peanuts than bagels, I say that's a positive tensor polarization. If I have an equal number across all three, it's unpolarized or zero polarization. And if I have more bagels than peanuts, I have a negative tensor polarization. So why do I find this really interesting? Well, building a target that lets us manipulate the spin shape, we can use as a new kind of probe to look at novel properties of protons and neutrons and the things that make them up. So, structure functions, we mentioned polarizing them gives us two more. With tensor polarization, we get another 1, 2, 3, 4 structure functions that we are looking at measuring. I'm going to focus on just the first one of these, B1, because that's right now the only one that we have a measurement of. What's interesting here at this high X region, remember that's momentum fraction to a proton, is that all conventional nuclear physics models expect this to be very close to zero in this higher X region. And the data that we have from a previous accelerator showed something very, very different here. This does not agree with our standard models of nuclear physics. But the error bars are big, so maybe it's just a statistical fluctuation. We don't know. So we're working on a measurement to redo this measurement to much higher precision. There's a lot of interesting things going on here that I'm not going to have time to go into detail, but basically there's a bunch of different models that if we find with our high precision measurement, we confirm that this is not only not zero, but negative. That is going to open up a whole new branch of study of how we understand the quarks inside of protons and neutrons the same way that those G1, G2 structure functions did with the spin crisis. We're actually hoping that this will give us some light for helping to solve that spin crisis. There's also another interesting thing in nuclear physics called short-range correlation. So the way I like to think about this is that everything looks like deuterons. Everything looks like my bagels. This is my everything bagel. If we take those cross-sections I mentioned before, for nuclei from light things like helium through beryllium through copper, which makes up a bunch of us, or carbon, copper, up through gold, this flat region in all of them are regions where they look like deuterons. We don't fully know why this happens. We have a sense of why we think it does, and we're learning more about it every year. But I have an experiment that is going to be looking at this directly, of why these things look like my bagels. Why does everything look like a bagel? And it goes back to that paper I mentioned from Hofstadter, who pointed out that it'd be interesting to look at that simplest composite nuclear system, one proton, one neutron. So that's what we're going to do. We're going to build this new target. We're going to go to a kinematic range to really probe what is happening here. The interesting thing we're going to learn from this is information about how hard or soft the wave function is. It's a bunch of complicated words. Think of the hole in my bagel. If the hole is very well-defined and sharp, that would be what is a harder wave function. If it is a very slow, broad hole that kind of goes into it gently, that would be a softer wave function. And this experiment we're doing will tell us whether that is a well-defined sharp hole or a more broad, fuzzier hole inside of my deuteron bagel. This measurement is going to be the first one to do this. There's no existing data within this kinematic region of this observable. All of these different colored plots on here are theory estimates for what different people think it will be. And the fact that there's this huge range between them all really says that we don't know what's going on here. And we need an experiment in order to figure it out. And as an experimental nuclear physicist, you know, that's my jam. That's what I go for. So we have this experiment that we are working hard on running in the near future. And I mentioned that this is important for their short-range correlations because everything looks like my bagels, even up to the heaviest nuclei, like gold and things, you know, way at the end of the periodic table. It actually extends way beyond that to the super heaviest of nuclei, neutron stars. The structure of neutron stars, some of the weirdest, most exotic pieces of matter we have in the universe, depend on the properties of that bagel's hole. And if we can learn more about the bagel's hole, we can learn more about almost every nuclei on the periodic table and about how these strange things up in space, spinning around rapidly, wild magnetic fields, when they were first discovered, were called LGM for little green men. We really want to learn more about how they work. And this experiment and others will tell us a little bit more about that. So that's kind of my brief 100-year history of nuclear physics, where we started, where we came from today. And of course, this work would not be possible without the many students, colleagues, postdocs. So many people work on these experiments, as I mentioned before. This is but a subset of us who are at the University of New Hampshire working on this. We have colleagues at University of Virginia and across the world without whom this entire effort would not be possible. So with that, I will say thank you, and I look forward to watching a movie about bagels with you soon.
So everyone, please join me in thanking Dr. Elena Long. few questions. I assume there will be a few, yeah? So who has a question? Yeah.
Hi. Do we have any idea what would happen to a nucleus if it went through a black hole, or when black holes, take up old stars? What happens to their
Weird things. First off, I want to mention that the hole in my bagel helps stop every nuclei in our body from itself collapsing into a black hole. So that's part of how we're stable. Black holes form when even that strong nuclear force is overcome by gravity. I do a lot of work in nuclear physics where effects of gravity are often ignored, and there are even those in my field who will chat occasionally about whether or not it's a real force or something else because of how often we ignore it in the work that we do. Crossing over the Schwarzschild radius, the event horizon of a black hole, we don't fully understand what happens. We need young new scientists to help join our physics effort to help us answer that question because we don't fully know. One of the weird things that looks like it may happen in certain cases, to give you a flavor of the sense of the problems, is for a static, non-rotating black hole crossing over this event horizon, it seems like one of the dimensions of space will turn into a dimension of time and vice versa, and interpreting what that actually means for the structure of reality is difficult. And we don't fully know what's going on there. And we really need new talent within physics. We need those of you interested in studying this to really come help us to further our understanding on that.
Who next? Who has another question?
So I've heard of CERN, and I've heard of stuff out in Stanford. I've never heard of Jefferson facility. Have you talked about that?
Yeah, absolutely. So with working at CERN, the way that we like to talk about laboratories at that is pushing what is called the high energy frontier. So CERN is way bigger than Jefferson Lab is. They can accelerate things to way higher energy than Jefferson Lab can. And hitting things with higher and higher energy can create new particles. Higgs boson going into particle physics is that avenue. Jefferson Lab is a little bit different in that our area of expertise is studying protons and neutrons, not creating these new states, but really trying to fully understand this basic thing that is in all of us and makes up everything we interact with just about on a regular basis. We are at Jefferson Lab what we like to call the high intensity frontier. So in order to do these measurements, to pull out these really small subtle effects, we need to be able to send in a massive number of particles to do it. So our luminosity, the amount of particles we're sending in compared to the amount of things that we're hitting, is orders of magnitude higher than what CERN has. Our energy is not. CERN definitely beats JLab on the energy frontier, but on the intensity frontier, that's really where labs like Jefferson Lab come into play and do our work. A number of different sources fund it. National Science Foundation is a big funder of it. Department of Energy is an extremely significant funder of it. The Department of Energy is the main funder of the work that I, in particular, in my lab, has been doing.
We have time for one more.
When you say that a quark appears and disappears, how is that something that's possible? My understanding is that things can change, but it all exists.
I love this question. In short, quantum mechanics is weird. So what's happening, anything that we think of as a vacuum is a region of space that has nothing in it. And as we kind of probe that deeper and try to look for things in a vacuum, one way of doing that is looking in regions, near black holes. If there is nothing near a black hole, then there should be nothing in that vacuum around it. In a vacuum, we have never found nothing. We get particle-antiparticle pairs that will briefly pop into existence, and they do so in accordance with the Heisenberg uncertainty principle. So you might be familiar with that as the uncertainty in position times the uncertainty in momentum is greater than or equal to a constant, a number, meaning it's not zero. You can play with math a little bit to rearrange that and instead make it uncertainty in energy times uncertainty in time is greater than or equal to that same non-zero constant. From Einstein, we learn E equals mc squared. Energy and mass are the same thing. That asterisk I had in the beginning, the energy is always there. It's the particles that are coming in and out. So since energy and mass are just two different sides of the same coin, that energy can come in, and the amount of mass, the amount of energy that comes into existence can only exist relative to the time frame in that same equation greater than or equal to that non-zero constant. So you can have something very massive exist for a very short amount of time, or something very light exist for a longer amount of time, but it's all related through the Heisenberg uncertainty principle, which itself comes down into that category of quantum mechanics is weird, and you should all read about it because it's really cool.
That is amazing. My mind is just racing. I'm sure that once I process, I'll have many, many more questions for you. But please join me again in thanking Dr. Elena Long.
Thank you very much.
And just to let you know a little bit about what we're doing here as part of this program, the Science on Screen program is funded in part by a grant from the Sloan Foundation. And part of what we need to do for the terms of that grant is that we film tonight's proceeding. So everyone, thank you to Flume Media for being here and filming it.